Okay, so today we're doing our recitation for looking at surface integrals and how to do them and how to do them using Stokes' theorem in particular, but more importantly, when to know when to use Stokes' theorem. So I mentioned this last week, but now that we've got a little more knowledge about what surface integrals are and how to do them, I want to reintroduce this, what I call the four most important principles of integration. And if you stick to these four principles, then everything else should be really straightforward. And the first three of these principles, in my opinion, are not very difficult. The first of them is just syntax. I mentioned this last time. Whatever you're working with should end up as a scalar, not as a vector. And the only exception to that is if you're trying to find the position or velocity of a moving particle if you're given the velocity or acceleration, respectively. So in particular, that means make sure that whatever you're doing is crossing your vectors and differential operators or dotting them appropriately. So make sure that then you're doing the right kind of stuff with them. And you've got dimension is the second principle. And what I mean by dimension is the following numbers all have to be the same. First of all is the number of size dimensions of your space. And when I say size dimensions, what I mean by that is, well, curves, for example, have length. Well, lines have length. Length is a one-dimensional size measurement. Surfaces, meanwhile, have area, and area is a two-dimensional size measurement. And solid objects have volume, which is a three-dimensional size measurement. So that's what I call size dimensions. So curves have one size dimension, surfaces have two size dimensions, and volumes and solid objects have three size dimensions. Some people call these degrees of freedom as well. They mean the same thing. The second number, which is the same as the first one, has to be the number of integrals you have to do when you iterate it. So for example, surfaces, you do two integrals. Curves, you do one integral. Volumes, you do three integrals. Corresponding to, you're adding up area bits, right, or volume bits, and it's length times width, or length times width times height, as whatever the case may be. The third number, which is related to this, is the number of single variable differentials that you have when you actually iterate it. So when I say single variable differentials, I mean for curves, that's dt or dx. For surfaces, it's du and dv, right? You've got du dv, or perhaps dx dy. And for volumes, usually it's going to be dx dy dz, or d rho d phi d theta if you're in spherical coordinates, for example. And the fourth number, which again has to be the same as all of these others, is the number of variables that you actually have to integrate. And if you compare the third and fourth of these items, the number of single variable differentials and the number of variables you actually have to integrate, then, well, of course, those numbers are going to be the same. So if you think about what all these things mean, and if you think about single variable differentials as small changes in length or width or height, then yes, of course, the size dimensions have to be equal to the number of variables that you're integrating over. If you just think about what integrals actually mean. So syntax and dimension, relatively straightforward. And stretch factor. And the stretch factor before the differentials is usually going to be, not usually, it's always going to be a derivative of the parameterization of the curves or the surface. For example, r prime t or ru cross rv for surfaces. And in the case of spherical or cylindrical coordinates, or cylindrical or spherical coordinates, just to keep my my verbiage and my slides consistent. For cylindrical coordinates, you're going to introduce an extra factor of r. That's your stretch factor. And for spherical coordinates, you're going to introduce an extra factor of rho squared sine phi. So these are the first three principles. And then there's the fourth principle of integration, which is the most important one in terms of all these theorems that we're working with. An nth integral of a derivative removes the derivative and does an n-1 integral on the boundary, which sounds really weird. It sounds like, what do you mean an nth integral? Well, again, that nth integral is the same thing as however many integrals you have. So, for example, if you're doing we just learned this as Stokes' theorem. If you're doing a double integral, right, a second integral on a surface with a boundary, and you're integrating a quote-unquote derivative of a vector field, which in this case means curl, then that's just an n-1 integral, or in this case, you started with a 2 integral, you integrate a derivative, you go down to a 1 integral on the boundary, right? On the boundary of that surface, which is just the boundary curve. And you do it with an undifferentiated vector field. That's Stokes' theorem. That's his last item here. And that's the exact same thing as the fundamental theorem of calculus. For example, if you do it, you think about that as a one integral, of course, and you integrate a derivative in the most obvious sense, well, then all you're going to do is take the n minus 1 integral, or in this case, that means a 0 integral on the boundary. And yes, that means we literally think about fb minus fa as a 0 integral, like a zero-dimensional integral on the boundary of this region. And meanwhile, you have the integral over c of the gradient of f, and that's the fundamental theorem of line integrals. That's the undifferentiated version, is f at the end minus f at the start. And again, thinking about that as a 0 integral, that works out. And then you've got Green's theorem, which is an R2 version of Stokes' theorem, basically, where if you take this mysterious, weirdly differential-looking thing on the inside, you take a double integral over some region D. Well, that's the same thing as taking the integral of the appropriate vector field on the boundary. So what this really comes down to is whenever you're doing an integral, very often there will be a way of adding an integral to it, and there'll be a way of removing an integral from it. And sometimes you can use them, sometimes you can't. It depends on the specific circumstances. But it's important to be aware of all the different formulas that you have at your disposal and when you can use which ones. So let's do an example here. Let's start off by trying to calculate the integral over s of y squared z squared ds, where s is the part of this cone, y equals root x squared plus z squared, with y between 0 and 5. Now, we should observe in this case that this is a scalar integral, right? So we're integrating a scalar function. One second. We're integrating a scalar function that's given by f of xy equals y squared plus, what did I say plus? Y squared times z squared. So the only formula that we have for this, for scalar integrals, is the direct approach, where you take f of RUV, whatever u and v may be, times the magnitude of RU cross RV. Even here, though, even though this isn't a vector field, we're still applying, our principles of integration. We know that this is certainly not going to be f of R of uv times RU cross RV. It's certainly not that, because that would be scalar multiplication, because this quantity inside of here, inside of the absolute values, inside of that thing is a vector. But on the outside, we want it to be a scalar, right? So it's important to be aware of what our principles of integration are telling us in each of these cases. Now, in this case, we need to know what RU, RV is. So what exactly is that cone going to be? So how do we parameterize that cone? Well, we can parameterize that cone, for example, by saying that that cone is going to be the graph, right, of the function g xz equals root x squared plus z squared with over the region x squared plus z squared is less than or equal to 25. 25, where did that 25 come from? Well, it came from the fact that we're working with y between 0 and 5. And if we're looking at where in the xz plane, in the xz plane that's going to give us, that's going to be a circle or a disk of radius 5. So x squared plus z squared is less than or equal to 25 in that case. So there are two ways of going forward at this point. You can either use that formula, or but I prefer not to do that, though. And the reason I don't want to do that is because I don't want to have to deal with square roots. And I think square roots are annoying. So we can instead say that it's the graph of g of r cos theta, r sine theta, right? Which is, in this case, just going to be r. And let me actually, just to make a point even more clear, let me actually change the variables. It doesn't actually matter, but actually, I take it back. I'll keep those things as they were. But what I am going to say is that we can let r of uv, in the x-coordinate we're going to have r, in the x-coordinate we're going to have u cosine v. In the y-coordinate we're going to have, we're just going to have u. And in the z-coordinate we're going to have u sine v. Now compare that to what we would have, which is r cosine theta, r for y, and r sine theta, right? It's the same exact thing using u equals r and v equals theta. My point is you can do this in either way. I mean, the universe really doesn't care about what symbols you use for what you're plugging into this parameterization. So, but we calculate, but I'm going to use u and v only because I don't want to have to write r sub r. That's going to look confusing. So with this in mind, we can say that r of u cross r v, ru is cos v 1 sine v, negative u sine v, 0 u cosine v. Put your ijk's, and there you take this cross product. And what do you get? You get u cosine v I minus uj plus u sine v k. And if you take that and you dot it with the with both ru and rv, you'll find that yes, you do in fact get exactly what you want. So that's our cross product, and that's what we want. So now we're going to take the magnitude of that thing, ru cross rv, square root of u squared cos squared v plus u squared. Did I make a mistake? No, I didn't make a mistake. We're good. Plus u squared plus u squared sine v, which is going to come out to u times root 2. Okay? Okay, so I'm going to erase some stuff for a second just so I can make some room. Come on. Hold on a second. Wait a minute. So just to recap, we have that our parameterization is given by x equals u cosine v, y equals u, and z equals u sine v for u between 0 and 5, and v between 0 and 2 pi. So that's good. And from there, what we're going to be able to say is, okay, well, we also know that ru cross rv has a magnitude of u times the square root of 2. So all of that's very helpful. Now, meanwhile, we have f of r of u and v. Now, y is just u, so it's going to be u squared times z squared, which is u sine v squared, or in other words, u cubed sine squared v. And now we're pretty much ready to actually do this integral. So this is the integral from 0 to 5, integral from 0 to 2 pi of u to the 4th Actually, I'll be a little more specific here and say root 2 times u to the 4th sine squared of v, because we're multiplying f of r of uv times magnitude ru cross rv dv du. And we can separate this. We can separate this out into root 2 over 5 u to the 5th from 0 to 5. That's the first integral, times the integral from 0 to 2 pi of sine squared v dv. Let me make this a little bit easier, and I'll say that u to the 5th, what is u to the 5th? U to the 4th is 625. 625 times 5, 25 times 5 is 125 times, I believe it's 3,125 root 2 over, actually it doesn't even matter because this is just going to become 625. Sorry, let me do this again. Because it doesn't matter, but it's going to become, here's u to the 5th. It becomes 625 root 2 integral from, because you're dividing by 5 anyways, 0 to 2 pi of sine squared v dv. Now, here you want to use one of your trig identities that we had before. Oh, oops, 625 root 2. You want to use one of the trig identities we had before, which is that sine squared of v is 1/2 times 1 minus cosine of 2v dv. Now, cosine of 2v, that's going to vanish once you anti-differentiate that and apply and integrate from 0 to 2 pi. So we're just left with 1/2. So this whole thing, at the end of the day, is going to become 625 root 2 times pi. So there's our answer. Now, we couldn't use Stokes' theorem here because Stokes' theorem doesn't apply. Stokes' theorem only works for vector fields, and we're integrating a scalar function, so that was never going to be an option here. But now you can also do this using Cartesian coordinates. It's just that I chose not to because I recognize, well, wait a second, this is this is a cone, and that cone might become a little bit annoying to differentiate once you actually start having to do that. So just using polar coordinates or sort of tilted cylindrical coordinates, I think, is a lot easier for this problem. And here's something a little bit different. So what if you want to find the work integral, the single line integral, f dot dr, where f x y z is given by x squared y I plus 1/3 x cubed j plus x y k, and c is the curve of intersection of the hyperboloid z equals y squared minus x squared, and the cylinder x squared plus y squared equals 1. Oriented counterclockwise as viewed from above. Now, do I expect everyone to draw this exactly? No, of course not. I'm going to do it anyways, just so that we can get a bit of a better idea of what this thing actually looks like. It wasn't a very good drawing of hyperbole. Let me try that again. It's something like this, right? Here's our hyperboloid. Right? But it's sitting inside, but inside of this hyperboloid, inside of that hyperboloid is going to be some other cylinder, which I'm going to draw in pink. Right? Try it again. So it's going to create some kind of a weird surface thing. Through that hyperboloid. Now, do I expect you to be a perfect artist? No, of course not. I mean, look at this. That artwork that I just drew there is a piece of garbage. But you should try to have an idea about what this thing looks like. In this case, we're looking at something that I think it's kind of like this sort of a Pringle chip looking thing, in a way, where you've got this, where you've got sort of a something like that. We're basically looking at this thing that looks kind of like a Pringle chip or this infinity sign. So we're trying to find the, so here in this case is
our curve. Our curve is this curve of intersection of these two things. Oriented counterclockwise as viewed from above, and if you were to view that from above, then you can believe me, hopefully, that means we're oriented in this direction. Now, this is a kind of difficult thing to draw and to visualize, but you should try to have a sense of what this thing looks like. You know, it's not terribly hard to visualize without drawing it, but really make an effort to understand what this thing looks like. And if you do that, then we're trying to do this thing. First of all, the question is, well, if we're trying to find this work integral, there are basically three options. There are three different strategies that we can use. You can either add an integral, which is Stokes' theorem, which is to say that this curve over f dot dr is the double integral over some surface of the curl of f dot ds for the right surface. You have to choose your surface, though. You can remove an integral, which is the fundamental theorem of line integrals. And if you remove an integral, that means that you'd have to have that your vector field in question is actually the gradient of some potential function, some anti-gradient. But that's not super obvious. I don't know if it is. And in fact, we'll be able to tell pretty quickly, no, it is not. Or you can do the direct approach. The direct approach is just that the integral of f dot dr is the integral over, from a to b of f of r of t dot r prime of t dt. So you want to use one of these three strategies. So which one is it going to be? And in this case, we're going to want to use, well, let's think about this for a little bit. Can we remove an integral? And to remove an integral, we need it to be the case that our vector field is conservative. Or in the three-dimensional case, that means that the curl has to be 0. So is the curl 0? Well, the curl of f is, so we can look at that, that's del x, del y, del z, x squared y, 1/3 x cubed xy. What does this come out to? In the I direction, we're going to get xi. J, we're going to get, j, we're going to get minus yj. In the k direction, and then in the k direction, it's going to become x squared minus x squared. Okay, or in other words, just xi minus yj. So let me erase some stuff to recap for a second. So the bad news, one second. So the bad news is that the curl, we now know, is xi minus yj. Well, obviously that's not 0. So the fundamental theorem of line integrals is not going to be an option for us. But on the other hand, that curl is very nice. That's a very nice curl in this case. And I basically already drawn it, but you notice that this curve is the boundary of the graph, right? It's the graph of the function gxy equals x squared minus y squared. Oh, sorry, other way around. Y squared minus x squared. On the disk, x squared plus y squared is less than or equal to 1. So we might consider using Stokes' theorem instead. So let's try that. Okay, we've got that the curl is xi minus yj, and we've got that C is the boundary of the curve parameterized, boundary, not curve, surface parameterized by the function rxy equals x comma y squared minus x squared. And to be clear, this is going to be our surface S. So we're going to need to know what the cross product of this thing is. And maybe you forgot what the cross product strategy is, that little shortcut, quote unquote. That's okay. It's not hard to work out explicitly. 1, 0, negative 2x, 0, 1, negative 2y. Sorry, not negative 2y. That one's just 2y. I, j, k. Which, in other words, is going to be 2x I minus 2y j plus k. And meanwhile, the curl is almost as easy as you can possibly want it to be, because x and y in our parameterization are just x and y. So the curl in this case, what we want is the curl dotted with, and what we really want here is the curl dotted with Rx cross Ry, which is just going to be 2 plus 2, or 4. Aha. So what we get actually is that this this work integral f dot dr is the double integral over S of the constant function, the double integral, not over S, of, I'll write it out explicitly. Nabla cross f dot ds, which we just found is the double integral over the appropriate region D. And by the way, D, which is the domain of integration, is all x and y, so that x squared plus y squared is less than or equal to 1. Right? So of the function 4, dA, or in other words, 4 times the area of D. The area of D is just pi, so the whole thing comes out to be 4 pi. Now that's a nice result. Now, can you do this without using Stokes' theorem? Could you have done this directly? Yeah, you can, but that's going to be a really nasty integral, right? I mean, just look at that for a second. You're going to get, you're going to have to do, let's just see what that would look like. So that's 4 pi. That's the answer at the end of the day. So if you try doing this directly, what would this give you? This would give you that, you would need to have that RT, well, it's over a circle, so you can say that RT is cosine t, sine squared t minus cosine squared t. If you're very good, you can you might notice that there's a trig identity there, which is cosine t, sine t, negative 2 cosine. Negative cosine 2t, and maybe that will make your life a little bit easier. But even still, what this comes out to is that r prime of t is negative cosine t I plus, oh, sorry, that was wrong. Negative sine t I plus cosine t j plus 2 sine 2t k. And what do we end up with in this case? What we're going to get is that, now meanwhile, f of r of t, get ready for this. This is going to be cosine squared t times sine t I plus 1/3 cosine cubed t j plus cosine t sine t k. So when you dot those things, what you want to do is you're going to have to integrate from 0 to 2 pi of the dot product of these things, which is going to be negative sine squared t cosine squared t plus 1/3 cosine to the 4th t plus 2 sine 2t times cosine t sine t dt. That's what you're going to have to integrate if you try doing this directly, which is really crappy. So we're not going to do that. And if you tried doing that, then that would work very badly out on when it comes to exam time. So don't do that. Instead, we're going to use Stokes' theorem to solve this because we can, because the curve in this case is closed. The curve is closed, and the curl of the vector field is much nicer than the vector field itself. So every now and then, Stokes' theorem comes in real handy for things like this. All right, but you can't always use Stokes' theorem. So here's an example where you can't use it. And why do we know that we can't use it? Well, let's try this out. What we know is that what we have here in this case is, again, you have 3 options. So well, actually, we haven't looked at how you add an integral yet, but basically for now we have only 2 options. Okay, I won't lie to you guys about this. You do have 3 options. It's just that one of them we haven't seen yet, but that's okay. We're not going to use it anyways. There's removing an integral, which again is Stokes' theorem. And by the way, as you're doing this, do you have to write out all these formulas explicitly? No, I just like doing that because I like seeing what my options are and what I can use. So you can remove an integral, you can add an integral, which we haven't done yet in this class, but that's going to be next week. That's the divergence theorem. Or there's the direct approach. Which is equal to number d f dA. So which of these are we going to end up doing? Well, can we use Stokes' theorem? Is that an option for us? Well, your surface is nice. It's a radius. It's a sphere with radius 1 and center the origin. A couple issues though with Stokes' theorem. The question that we need to ask ourselves is, what's C? What's our boundary curve? Well, the surface is a sphere with radius 1. What's the boundary of a sphere? And again, we're not talking about the ball. We're not talking about the surface. We're not talking about the surface boundary of the ball. We're just talking about the boundary of the surface itself. What's the boundary of the surface of a sphere? And if you think about that for a little bit, you might come to realize there isn't one. A sphere doesn't have a boundary. A sphere is a boundaryless surface. So in this case, we have that C is
empty. There is no boundary. So now that doesn't mean that you can't use Stokes' theorem, but you have to be really careful, because if we have, and I'll actually change part of what I wrote here, and I'll change this to G instead of, for some other vector field, G. So if we have that F is the curl of some vector field G, then as a consequence of this, we're going to have that the double integral over S of f dot ds, it's going to be 0 because there is no boundary. You're integrating over something that doesn't exist, and we say that that's 0. So that's the worst. So is that bad? No, but it should make you kind of suspicious about whether or not that's the right approach. The real issue here, though, with Stokes is not just that you don't have a boundary curve, it's also that I don't even know that that vector field is a curl. Is f equal to the curl of some other vector field in the first place? Well, the test for this is to tell what the divergence of f is, and the divergence of f is, in this case, 1 plus 1 plus 2z, which is 2 plus 2z, which is not 0. So no, we can't do that. It's not going to be an option for us. So we can't use we can't use Stokes' theorem here. It turns out we can use the divergence theorem in this case, but we haven't looked at what that is yet. So instead, we're just we're going to ignore the divergence theorem and say, okay, we're going to have to do this directly. So how do you do this directly? Well, we're going to need to know what the parameterization is of our surface. And the surface is a sphere, so we can use spherical coordinates to parameterize it. And it's parameterized by x equals cosine theta sine phi, y equals sine theta sine phi, z equals cosine phi for theta going from 0 to 2 pi, and phi going from 0 to pi. I didn't say this in the original problem, and I should have, but we'll assume in this case that we've got outward orientation. So we need to know what the we need to know what the cross product that we need is. So the cross product r theta cross r phi. How do you know if you need to do r theta cross r phi or r phi cross r theta? How do you know what the order is? Well, I'll show you how you know what the order is. Let's do r theta cross r phi and see what happens. R theta is negative sine theta sine phi, cosine theta sine phi, 0, not 6. Cosine theta sine, cosine theta cosine phi, sine theta cosine phi, negative sine phi. And you do this out, and what do you get? Well, what you're going to end up with is negative cosine theta sine squared phi I minus sine theta sine squared phi j. And in the k direction, you're going to get minus cosine phi sine phi k. Is that what we want? Is that outward or inward? Well, notice that that's the same thing as negative sine phi of cosine theta sine phi I plus sine
theta sine phi j plus cosine phi k. Or in other words, negative sine phi of r phi theta. Now, if you think about what a sphere has to look like, a sphere, you know, I didn't do a very good job of drawing this, but whatever. If you think about what a sphere is going to look like, what we have to have be the case is that our normal vector, right, because that's what this r theta cross r phi is. It's telling us the direction that we're going in. And we want this vector to be going outward, right? We want it to be outward oriented, which means that, and I'll draw that better in this case. We want that vector to be going outward. And if that vector is going outward, that means it's going to be a scaling of that point itself, right? It's going in the same direction. Well, here this is going to be less than, here this is going to be less than or equal to 0. So it's going in the opposite direction since since phi is between 0 and pi. So it's the opposite direction. Or in other words, the inward. So that's a problem. That's not going to give us the direction we want. But it's not a huge problem. So that's the wrong orientation, but we can fix the orientation by just orientation. I can't speak and write at the same time. You can fix the orientation, but just by saying that we're instead going to look at r phi cross r theta instead. And our phi cross r theta, well, that's just negative what we had before, sine phi r phi theta, which is going in the right direction. Or in other words, so let me just start. Let me just get rid of some stuff. A second. So in this case, we're going to have that r phi cross r theta. Excuse me one moment. There's a strange noise from outside. So we know what this is going to be. We know that our phi cross r theta is cosine theta sine squared phi I direction plus sine theta sine squared phi in the j direction plus cosine phi sine phi in the k direction. We just calculated this in the previous step. All right, so that's good. So we know what r phi cross r theta is. Now, meanwhile, we know that f of r of phi and theta, f of r phi and theta is going to be cosine theta sine phi I plus sine theta sine phi j plus cosine squared phi k. So we take the dot product, f of r phi theta dot r phi cross r theta. And what does that come out to? That's going to be cosine squared theta sine cubed phi plus sine squared theta sine cubed phi plus cosine cubed phi sine phi. Clean that up a little bit. This is sine cubed phi plus cosine cubed phi sine phi. Or in other words, sine phi times sine squared phi. Too many lines. Sine phi times sine squared phi cosine cubed phi. I keep on forgetting my operators. So now we're basically ready to do the integral. So this is the double integral over s of f dot ds, which is the integral from 0 to 2 pi of the integral from 0 to pi of sine cubed phi. I keep on doing that. Plus cosine cubed phi sine phi d phi d theta. One of the things you notice is that there are no theta terms, so that just leaves us with 2 pi integral from 0 to pi sine cubed phi d phi plus 2 pi integral 0 to 2 pi. Oh, sorry, no, 0 to pi, not 0 to 2 pi. Cosine cubed phi d phi. And just do those integrals. And the integral of sine cubed phi, well, that you can do a little trick for, which is to say, I'm actually going to erase some stuff to make room a little bit. So we get in this case is the, oops, wait a second. This is 2 pi, so just going all the way up from where we were before. This is 2 pi times the integral from 0 to pi of sine. The usual way to do this is sine of phi times 1 minus cosine squared phi. Because sine squared phi is 1 minus cosine squared phi, d phi. And the other one we can, oh, I left out, oopsie, I left out an important detail here. Plus 2 pi times integral from 0 to pi of cosine cubed phi sine phi d phi, which you can write as the integral from 0 to 2 pi of 1 minus cosine squared phi. Now you can use the u substitution in this case times negative 1/2 from 0 to pi, because if you differentiate this, then okay, well that's that's just the usual. Actually, hold on a second. I'm doing this in a slightly backwards way. Let me try that again. Got a little ahead of myself. Integral from 0 to pi sine phi d phi minus integral from 0 to pi, there we go, sine phi cosine squared phi d phi. Well, the integral from 0 to pi of sine of phi, what's that going to come out to? That's going to be 2 pi times negative cosine phi from 0 to pi plus, because when you anti-differentiate this, this is going to become plus 2 pi times 1/3 cosine cubed phi from 0 to pi plus 2 pi times negative 1/4 cosine to the 4th phi from 0 to pi. Whole thing basically is going to come out to 2 pi times, in the first case, cosine phi from pi to 0 is going to be 2 plus pi to 0 is going to be negative 2/3 in this case. It's cubed. Sorry, minus 2/4. So the whole thing basically is going to come out to 2 pi. And here's where I reveal that I actually don't know basic arithmetic. 24 minus, what is that? It's 24. No, I'm being stupid. 12 minus 6. So the whole thing comes out to 5 pi over 3. After you do the arithmetic, which I clearly don't know how to do. So that's all that this really comes down to. So now again, we can and we will use the divergence theorem to do this same exact problem next week, but you can do it either way. But you just can't use Stokes' theorem. So here's an instance where Stokes' theorem is not an option to us. Let's do one more. But sometimes Stokes' theorem is an option. And in this case, we can very clearly see it is because we have a curl sitting right inside of the integral, and that should scream to us, hey, maybe Stokes' theorem would be a good idea to use in some capacity. So what do we know in this case? Our surface is the cone, x equals root y squared plus z squared for x going from 0 to 2, oriented in the direction of the positive x-axis. So what does this look like? Well, our surface is going to look something like this. X is that cone. I'm going to draw our axes slightly skewed to make this a little easier to see what's going on. I'm sorry. I think I did that the wrong way. So here's going to be the y-axis. Here's going to be the x-axis. Our surface, in this case, is going to be this cone. Right? That's what we're interested in here. So, yep, I did that correctly. So, and that's just a simple rotation of our usual reference frame. But we know in this case that we have a boundary as well, right? It's the boundary of this thing is given by the edge of this cone. And because we know that we have that boundary, we can also say that we have another surface, namely this disk. So we can either use this cone, which we're calling S, this cone, which we're calling S, or we can use this, make it a bit bolder, or we can use this plane piece, which I'll call S prime. Both of them have the same boundary curve, which is C, oriented in the direction of the positive x-axis, which means that this cone is oriented pointing in this way. Now, if you want to orient our curve so that it's consistent, again, if you're a little person and you're running so that your curve, so that your surface is going to be on your left side, that means that it's going to be counterclockwise when viewed down the x-axis. So if it's counterclockwise when viewed down the x-axis, that means we're oriented this way for now. So because we're steering it in the opposite direction. It's counterclockwise when viewed down the x-axis. So it's a little hard to draw this in an easy way, but that's basically what we're working with. Maybe I can maybe I should have drawn it in the other reference frame to make it easier, but oh well. So pardon me. So what is the curl? Let's try calculating this curl in the first place and see what we get. Well, we've got del x, del y, del z, arctan x squared y z squared, x squared y, x squared z squared. What does that come out to? Well, the I direction is 0. J direction, that's z squared up there. So the I direction is going to be 0. In the j direction, we're going to get negative 2xz squared minus minus 2z over 1 plus x to the fourth y squared z to the fourth j, which looks a little scary, but it turns out this is not going to be very difficult at all if we're very clever with how we do this. And that's just the chain rule for the derivative of arctan. And then in the k direction, we're going to get 2xy, minus x squared z squared over 1 plus x to the fourth y squared z to the fourth in the k direction. Now that I'm staring at this, I'm realizing that I left out some stuff in this numerator up here, so I have to redo this a little bit. That's not 2z, it's actually going to be 2x squared yz squared up top. Now that's a little bit scary looking, and the original vector field is a little bit scary looking also, so neither of these are particularly friendly. However, if we parameterize s prime, what is this going to give us? And here's where it gets really, really awesome. If we parameterize s prime, what this means in this case is for s prime, that's given by, well, x is always going to be 2. Y is y, and z is z. So our y cross our z, in other words, the normal vector pointing out from that surface, the s prime surface, and we can see what that's going to be. That's going to be I. And now it's almost a joke. Now this is almost silly. So this double integral over s of the cross product, nabla cross f dot ds, well, that's just the same thing as the double integral over s prime of the curl dot ds. But we know what that is. That's the dot product of something with no I term with I. That that dot product, actually this should be over d, that dot product is 0. The whole thing's 0. So even though it looks very scary at first, as soon as you actually just stop and worry about and just look at, well, wait a minute, there's an easier surface we can work with. Why don't I just use that easier surface? Everything falls out in a much nicer way. So this is a very nice problem if you think carefully about how you go about doing it. All right, that's all I wanted to do for today. Thank you, everyone. Hopefully this was informative. And I will, and Joe will run the recitation on Friday, and I will talk to you guys next week. Adios.